Hello guys, Mr. G here, and we're going to be making another video related to vectors, and this is for the grade 11 mostly, but grade 12 may watch the videos. It will help them in most of the topics. Okay, so we're going to be talking about a new concept, and then we're going to be solving two questions. All right, first of all, we're going to be talking about a closed vector diagram when the forces are at equilibrium. Previously we learned about how to add vectors that are not at equilibrium. It means there are more than one force acting on an object. We're going to solve a question using that, and here is you can see all the notes, all the lessons we've been doing related to vectors. Now we're going to be talking about a closed diagram or a closed vector diagram, and we're going to be talking about equilibrium, which is in fact the same thing. So what do you need to know here? That if the system is at equilibrium, the net force is going to be equal to 0. So F net, or the net resultant vector, is going to be equal to 0. This is later on you're going to learn about the law, but for now we're going to see this one here. That means that the system is at equilibrium. Alright, so now what it means that is at equilibrium. If you have forces that act on an object and the object does not move, for example, let's see one picture here. For example, here we have a box which is hanging from the roof. The box is not moving, and if it's not moving, it's because the system is at equilibrium. This system is at equilibrium, and therefore for that system the net forces is going to be equal to 0. This later on you will learn it as Newton's first law. But what is the most important here? The system here, what forces are acting on that little box? The force of this cable A, this is the first force acting there. There is also B. There is also B acting on the box, but there is not also A and B. There is also weight. There's also weight acting on that block. This is W, and you will learn more about that also later on. Now, what you need to know here, if we draw a vector diagram, if we add all these vectors using the method tail to head, and this is not going to be accurate, if we add all those two vectors using the method tail to head, then we're going to have this one here, which you can see is a closed vector diagram. So the head of the last vector ends on the tail of the first vector, and this one here means that the system is at equilibrium, and therefore the net force is equal to 0. That is the meaning of that. That is a closed vector diagram. This is happening when the system is at equilibrium, and then you can see the triangle. The head of the last vector you draw will end on the tail of the first one. So the system is at equilibrium. Now, if we represent this one in the Cartesian plane, for example, if we have the Cartesian plane, this one, not at scale, those forces are on none of the axes, and as we always do, we have to get the components. And as we do before, we will have the applied force A, or the force A in X and force B in X. Now, because the system is at equilibrium, you need to know that everything on the right here must be equal to everything on the left, because the system is at equilibrium. So that is very important, guys. And the same happens with up and down. So everything on top must be equal to everything at the bottom, and on top you can see that you have the two components, the A in Y and the B in Y, and the addition of both of them must be equal to W. And this is the first concept I wanted to speak with that we didn't speak before, and we're going to need it for the next questions we are going to do. So this is all about vector. There is only going to be now some questions. We're going to make solve two questions now, then we're going to make another video in which we're going to do an experiment to see this concept here. We're going to see it in an experiment, and then we're going to do more questions, and the topic of vectors is done. It is finito. So let's go to the first question we are going to solve, and this was a question paper previously. They say force F1 and F2 are drawn on the Cartesian plane in which 1 centimeter represents 10 Newton. And this one is an important data in this question because the question is a little bit tricky. See Cartesian plane below. And this is the Cartesian plane. You have the Cartesian plane. Now note, this is centimeters, but the forces are not in centimeters. So if we come here back to this part, you need to know that 1 centimeter is equivalent to 10 newtons. And therefore, for example, in this picture here, 3 centimeters will be equal to 30 newtons. So that is what you must know, because the forces are in newton, not in centimeter. The centimeter was just the scale used to draw the vectors on the Cartesian plane. Now 1.1, use calculation to determine each of the following: the magnitude of vector f1, which is there, the direction of f2 measured from the positive x-axis, we're going to talk about that one, and use the component method to calculate the magnitude and direction of the resultant of vectors f1 and f2. So let's start solving question 1.1.1. Now they wanted to calculate the magnitude of f1. What do we know for f1? For f1 we have the horizontal component and we have the vertical component, guys. It's very simple. So we are going to use Pythagoras. Okay, so to calculate f1, all we are going to do is to use Pythagoras. So we're going to say f1 to the power 2 is equal to f1 in x, which is known for us, plus f2 in x squared. This is Pythagoras. Okay, so f1 squared is equal to 30. Note it is 3 there, but we are working with newtons, and that was the first thing I did right there. So 3, but it becomes 30 newton. So 30 newton square plus 10 newton square. No, you don't have to substitute the minus, because at the end when you multiply by the same number, the answer will be positive. So f1 square will be equal to 1000. But the answer is a square root, so you have to find out the square root on both sides. So f1 will be equal to the square root of 1000, and the answer for f1 will be 31.62 newton. And that is the first question. That was what they asked you to calculate. It was the magnitude of the first force. That one is quite simple. Now, the second question, the direction of f2 measured from the positive x-axis. Now, from the positive x-axis, how are we measuring direction from the positive x-axis? Well, you are going to count anti-clockwise from x in this direction. So this is the direction that they want us to get. This is the direction from positive x-axis. This is from positive x-axis. So how do we get that one? Well, there is different options to do it. One of them is to calculate this little angle here, and then if you use that, then this direction here would be 90 degree, because this one is 90 degree, plus the little angle you calculate there. And that is what we are going to do. The other option that you can try is to calculate the other angle here, and then it's 180 minus that one. But let's use this one. So we have that the opposite side is 1 or 10. In this case, it does not really matter if you use 1 or 10, and the adjacent side is the 3 or 30. So we are going to solve that question real fast. This is question 1.1.2. And now they want the direction. So we are going to first of all calculate the little theta. That is equal to 10 to the minus 1 of opposite side divided by adjacent side. Okay? And if we go there, is equal to 10 of the minus 1 of opposite side was a 1. I'm not going to substitute the 10. I'm going to substitute the 1. And the adjacent was the 3. So if you solve this one, the answer would be 18.343 degrees. Now this one is not the final answer. Remember, the angle from the positive x-axis they want you would be then equal to a 90 degree plus the 18.43 you get. So the final answer here will be 108.43 43 degrees. And this direction is the one they asking because it is from the positive x-axis. So this is the first question. I hope you understand. Remember, they wanted clockwise or anti-clockwise, sorry, from the positive x is there. This angle here, so that angle was now calculated. And the final one is use a component method to calculate the magnitude and direction of the resultant of vectors f1 and f2. Now, how we do that? This is question 1.1.3. Now, to do that one, the first we need to go to do is to get the component of each vector. So for f1, we need f1 in x and f1 in y. For f2, we need the same, and those are given to us. So for f2, we need the same. We need f2 in x, and you need f2 in y. But they are given to us. It is in the graph, in the Cartesian plane. As you can see, they are all there given, all those components. So I'm just going to write it here. So here is the answer. Those are given to us. Now, what are we going to do then? Now we are going to get the resultant in the x-axis, and we are going to get the resultant in the y-axis, both of them. So for x, we have 30 from the first vector minus 10, which is 20 Newton. And for the ry, we have 30 for the second one minus 10 is equal to 20 Newton. This is very, very easy. So this is 20 Newton to the right, or to the positive x-axis. Positive x-axis. And here we have positive y-axis. So this is the two vectors we have. If we do a roughly sketch with this, what we have is this here. This one is 20 Newton up, and we have here another 20 Newton in that direction there. This is also 20 Newtons. Now, they ask us to calculate the resultant, where the resultant would be. The resultant would be, and this is a rough sketch, this is for us to have an idea. The resultant will be this vector here. So we need a vector and we need a direction. Okay, so how do we calculate that? Guys, we're using Pythagoras again. So FR, the magnitude of FR is equal to FR in x squared plus FR in y squared. Okay, and now if we substitute here, we have in that FR is equal to square root of 20 to the power 2 plus 20 to the power 2. And when you calculate this one, the answer would be 28,28 Newton. But you are not done. You are not done because you need the direction. And for the direction, we are going to calculate this angle here. And this angle is going to be from the positive x-axis. So let's calculate that angle, and it's the same as the previous time we did. So this angle is equal to 10 to the minus 1 of opposite side, which is 20, divided by adjacent side, which is also 20. When you solve this one is 45, sorry, that's not a 5, 45 degree. Now, what is the direction? 45 degree from the positive x-axis. Remember, from the positive x-axis, it means anti-clockwise from x. This here means that this angle is from the positive x-axis. That will be the direction. Okay, and then this question is done. Now we have here the magnitude of the vector, and then we have at the bottom here the direction of that vector. So this question is done. It was not that bad, guys. It is really not that bad. You just have to read very careful. Okay, so let's do another question which is going to be a little bit more challenging. And here is the question. This question says an object O of weight W supported by two inextensible cables A and B. Cable A is attached to the ceiling and cable B is attached to the wall as shown below. Tension in the cable A is 1200 Newton and the tension in cable B is unknown. ignore the mess of the cable. Now, if you come back here to this explanation when we started with this lesson, here is the same situation. We are going to work with an object that is at equilibrium. How do I know it's at equilibrium? Because the object is not moving, it's hanging there. Right? So as long as the object is not moving, then it's at equilibrium. There is another type of equilibrium, but another time we'll speak about that one there. What is the net force acting on an object? So we don't even have to continue reading. We can say that F net is equal to 0 because the object is at equilibrium. And remember, we said if the object is at equilibrium, the net force is equal to 0. Draw a force diagram to show all the forces acting on the object. So if we come here, let's solve that question quickly. This is the object. So what forces are acting there? We have here, this does not need to be accurately. We have here cable A, as you can see there. This is TA. In the other direction, in this direction, you have a TB, tension of the rope B, and then there is weight. There is always weight, which you later on are going to learn more about weight, but there is weight straight downward. That is the other force. So those are the only forces acting on this block or box. Okay, so that was 2.2. 2.3, calculate the tension in cable B. Now cable B is on that side there. Now let's quickly have a small Cartesian plane and let's draw the vector B and see what we have there. Okay, this is the same forces, but now instead of drawing it in the box, I'm drawing it on the Cartesian plane. Now let's quickly go to the picture and I want to show you something. In this case here, you have this angle, and that angle, if here is the axis, will correspond to this angle here because they are alternated between parallel. So let's go to this Cartesian plane I draw here and write this angle here, which is important. It's given to us, guys. This one is 70 degrees alternated between parallel. You can see it there. This line here, this line there is parallel to the y-axis here, and then this angle is equal to 70. And the same happen on A, and that one is important for later on. We have that if we do this one here, we have alternated between parallel, and therefore this angle here will be 40 degrees. So let's add it here in the Cartesian plane because we need to know what angles and what data we do have. This one is 40 degree. Now they ask us to calculate the magnitude of B. Alright, now how can we calculate the magnitude of B if we have that angle? We can use sine and we can also use cosine. Okay, but we don't have nothing else. We only have the magnitude of vector A, which is going to be 1200. So let's also write there A is equal to 1200 Newton. Now, what we know that the system is at equilibrium, and therefore, because the system is at equilibrium, we have that the component of the vector A in X must be equal to the component of vector B in X. Remember, I told you when we started this video, everything on the right will be equal to everything on the left because the system is at equilibrium. So, saying that, we can use then this force A to calculate the FA in X, which is equal to B, as you can see it here. So all we have to say is that this side here is the adjacent side to the triangle. You can see it there, and the adjacent side, so we can say that FA in X is equal to FA is adjacent side is cosine of 40 degree. And doing this one, we can get that is 1200 multiplied by cosine of 40 degree. The answer is 919.25 Newton. This is, as we said, the horizontal component of force A. But saying that, we can use it here. So now we know that the horizontal component FB in X is also going to be 919.25 because the system is at equilibrium. And then we come here and we use sine or cosine to calculate the magnitude of B. B will be the hypotenuse. And now note what you have is this side here, and this side here is the opposite to the angle we are working with. So be careful with the angle. This is simple maths, guys. So this angle will be the opposite side. This one is the hypotenuse. So having the hypotenuse on the opposite side, we can say that sine theta is equal to opposite side divided by hypotenuse. If we have the actual letters here, opposite side will be FB in X, and the hypotenuse will be FB. And now we can substitute the numbers we have. We can say that sin theta, which is 70 degree, is equal to FB in X, but FB in X is 919.25 divided by FB, which is what we are actually looking for. And if you rearrange this one, FB will be equal to 919.25 divided by sin 70 degree, and the answer would be 978.25 Newton, and that is the value for B. I hope it's clear the work. It's not that difficult. Only you need to do is to know that it's at equilibrium, and therefore the both sides, right and left, will be equal to each other. So that was question 2.3. Now question 2.4, calculate the magnitude of the weight. It have to be using the same principle here. Okay, so let's quickly look at that one. No, this one is 2.3, but here we're going to use the same drawing. Now what you need to know, the system is at equilibrium, so everything top must be equal to everything at the bottom. Now what do you have on top here? You have the vertical component of A. This one will be FA in Y, and you also have the vertical component of B. There we go. This one is FB in Y. So, and at the bottom we have W. So we have to know then that, question 2.4, we have to know that the addition of FA in Y plus FB in Y will be equal to W. Everything on the top must be equal to everything at the bottom, because the system is at equilibrium. And then, guys, we have all the data here. So FA in Y, in this case here, will be opposite. Note there, this will be the FA in Y, this one here, and it's opposite side. So FA in Y is equal to FA, because it's opposite, will be sin theta plus FB in Y. Now be careful, because the angle is that one there. So if the angle is this one here, then we are not talking about the opposite, we are talking about the adjacent side, plus FB cos the theta, which is in this case 70. So let's write the values here, don't you get confused, and that is equal to W. The rest is the substitution and the calculation, and let's do that quickly. And the answer for weight is going to be 1105.93 Newton. Guys, this is the end of this question. This question is one of the most difficult ones you can actually get in the exam related to vectors. Most of them will be more or less the same as this one. Next time we're going to do an experiment to see something similar to this one, and then we are done. Then maybe we'll do one question before we start with Newton's law. I hope you understand this question could be tricky, but please, you can interact, ask questions, suggest, and if you want a specific video, you can also ask me, and I'll try to do that one. Thank you for watching. Subscribe for the channel. I hope this is clear. I'll see you next time. Mr. G here.